In this last video of the quick sort lesson, I would like to address two implementation issues. So the first issue is about space complexity of the quick sort algorithm. So on one hand, when sorting an array by a quick sort algorithm, we do not use any additional space. We just partition the array and we swap elements inside the array. On the other hand, the quick sort algorithm is a recursive algorithm. And when we make a recursive call, we store some information on the stack, right? So on one hand, it is possible to show that the average recursion depth is logarithmic, meaning that we need only a logarithmic additional space. On the other hand, there is a very nice and elegant trick that allows to re-implement the quicksort algorithm such that its worst case space complexity is at most logarithmic. So for this, let's recall that the quicksort algorithm contains of the call to the partition procedure and then of two recursive calls. Right? So the situation when we have a recursive call in the end of the procedure is called tail recursion. And there is a known way to eliminate such a recursive call. Namely, instead of making this recursive call, let's just update. Well, in the second recursive call, we sort the right part of our array. I mean the part from index m plus 1 to index r. Instead of making this recursive call, let's replace the whole body just with a while loop. Then we make, inside this while loop, we call the partition procedure as shown on the slide. Then we make a recursive call to the left part, but instead of making the recursive call for the right part, we just update the value of L to be equal to m plus 1. So this just makes and then we go to the beginning of this while loop, and this essentially mimics our recursive call. So far, so good. We've just realized that we can eliminate the last recursive call. At the same time, let's also realize the following thing. In our quicksort algorithm, we first call the partition procedure, and then we make two recursive calls. And these two recursive calls are in a sense independent. Well, it doesn't matter which comes first, right? So they do not depend on each other. This means that we can as well eliminate a recursive call to the first part. Well, and this in turn means that we can always select which one to eliminate. And for us, it is better to remove a recursive call to a longer part. And this is why. If we always make a recursive call to an array which is shorter, then we make a recursive call to an array which is at least twice shorter than the initial array, right? And this in turn means that the depth of our recursion will be at most logarithmic, because, well, the first recursive call is made for an array of size at most n over 2, then at most n over 4, and so on. So the depth is logarithmic, which is good. And this can be implemented as follows. So we first call the partition procedure. It gives us the value. It gives us the value of m. At this point, we know the lengths of two parts, and we just compare them. If, for example, the length of the first part is shorter, then we make a recursive call to this part, and instead of making the recursive call for the second part, we just update the value of L. In the other case, when the right part is shorter, we make the recursive call for this part, and instead of making the recursive call for this part, we just update the value of R. Right? So overall, this gives us an implementation of the quicksort algorithm, which uses, in the worst case, an additional logarithmic space. So the next implementation issue concerns the random bits used by our algorithm. So assume that we would like to have a deterministic version of our randomized quicksort. And this is a reasonable thing to want, because in practice we would like to have such a thing as reproducibility, which is, for example, essential for debugging. So we would like our program to always output the same on the same data set. And this is why we probably would not like to use random numbers. Okay? Then we can do the following. The following algorithm is known as intrasort and is used in many practical implementation of quicksort. So instead of selecting the pivot element randomly, let's select it as follows, using, for example, the following simple heuristic. Each time when we are given a subarray and we need to partition it with respect to some pivot, so for this we need to select pivot, and let's select it as follows. We take the first element of this subarray, the last element, and the middle element, for example. Then we have three elements and we sort them. We just compare them and we select the minimum or the medium value of this. And we use this element as our pivot element. So this is a very simple heuristic, right? It can be implemented very efficiently. We just need like three comparisons to select this median. And in many cases, this is enough for the quicksort algorithm to work efficiently. However, this is not what we want, right? We are not happy with the statement that this algorithm works well in many cases. We would like our algorithm to work well just on every possible input. Unfortunately, there are pathological cases in which these heuristics works badly. But we can overcome this in the following way. Let's, while running our quicksort algorithm, let's count what is the current depth of our recursion tree. And at some point, when it exceeds some value c log n for some constant c, then we just stop the current algorithm and switch to some other algorithm. For example, for the heap sort algorithm. This is another efficient algorithm, which is asymptotically as good as quicksort and merge sort. I mean, it has asymptotic running time n log n. However, quicksort is usually faster in practice. So at this point, we switch to the quicksort algorithm, which means that for these pathological bad instances, for the quicksort with this simple heuristic of selecting the pivot element, we still work in the worst case in time n log n. Because before we exceeded the depth c log n, we spent time n log n. And after this, we stop this algorithm immediately and we run the heap sort algorithm. So overall, we spend time n log n. So this gives us an algorithm which in many cases performs like the quicksort algorithm, and in any case, just in the worst case, its running time is bounded above by n log n. So to conclude, the quicksort algorithm is a comparison-based algorithm whose running time is big O of n log n in the average case and big O of n squared in the worst case. What is important in this algorithm is that it is very efficient in practice. It is more efficient than the merge sort algorithm, for example. For this reason, it is commonly used in practice, and for this reason, it is called quicksort.